another ZI atomic test is history now. Past history for the record books and live history for future planning. It was a double-header test like Buster Jangle and Tumbler Snapper, covering both weapon development and civil and military effects. And in some ways, it was our biggest research job so far. The preparation job was big too. Many hundreds of tons of material and months of intense planning and labor by skilled personnel were the ingredients, poured into a gigantic test tube, our Nevada proving grounds. In the spring of 1953, the mixture boiled up in a series of 11 atomic detonations. Operation Upshot-Knothole. The residue or end product of the reaction was knowledge, some of it in a yes or no form, immediately useful, and some of it requiring detailed analysis. The funnel into our Nevada test tube was the same old road up from Las Vegas. Nearly 80 miles of standard desert road which carries very little traffic when the proving grounds are quiet. Indian Springs was still primarily an Air Force support station for atomic test operations. The Desert Rock Troop encampment was in the same old place off to the left, after we turned off Highway 95. Inside the check gate and Mercury were living and technical areas and the field headquarters of the main test organization, a joint AEC and Department of Defense activity. From Mercury, the road goes roughly northward. It cuts through one range of hills. On across the valley of Frenchman Flat, then heads up into a notch in a second range. In this notch is the CP, the control point, the real nerve center and communications hub of the test site. This was the test manager's forward headquarters for the series, and primarily the center of operations for the weapons development program, Upshot. Looking out from the control point, an observer can see both of the major blast areas. Frenchman Flat, a dry lake bed, is still visible back in the valley we just crossed, though the actual ground zero point can't be seen. Yucca Flat lies on northward, in the next valley beyond the control point. 9 of Upshot-Knothole's 11 shots were fired out here on Yucca between March 17th and June 4th. These 9, 7 tower shots and 2 airdrops, were the AEC's weapon development tests. While such tests are not the main point of this film, their trend, the goals they're aimed at, are ultimately of great importance to the military services. So since these tests are primarily the concern of Los Alamos scientific laboratories, we turn to Los Alamos for an outline of the concepts and the objectives involved.
As usual, we're up to our necks, unraveling what happened in the last tests and getting ready for the next ones. Now, this weapon development business. We've been getting together some material for brief orientation talks. I want to emphasize that the amount of discussion given each shot is no indication of its actual importance. In fact, I may have to say least about some of the most important shots. Shot number 2 had for its source of energy a boosted fission device. It was part of a development that we think will eventually give us a weapon of approximately 30 inches in diameter. 3,000 to 4,000 pounds weight and a yield in the neighborhood of 500 kilotons, around 35 times that of the Hiroshima bomb. The next development shots were 3 and 5. Shot number 4, it was the first airdrop on Upshot and was detonated at approximately 6,000 feet, the highest burst of any gadget we've ever fired. So, once over lightly at least, that winds up the story of Operation Upshot-Knothole's weapon development program.
But outside of any discussion, outside of the laboratories, out on the Nevada proving ground itself, there was a great deal more to consider than the basic ideas back of the upshot firings. There was the same old job, complex and vitally necessary, of diagnosing the actual performance of gadgets being tested. Gadgets designed by Los Alamos and by Project Whitney of the University of California Radiation Laboratory. It's an old story, in a sense, to those of us in the services who have watched and assisted the preparation of previous tests. But that doesn't alter its prime value. To get the inside dope on the behavior of any experimental fission device, the scientists always want at least the answer to one classical three-headed question. What was the alpha rate, the transit time, and the yield? And yield alone is computed and cross-checked in many ways. Probably most accurately by radiochemical analysis of cloud material collected by the sampling planes, and by ultra-high-speed photography of fireball growth. Another Nevada activity of the AEC was its civil effects program of tests originated by various non-military federal agencies. For example, 2 typical frame houses were exposed to the first blast of the series for the Federal Civil Defense Administration. Some 50 civilian automobiles were included in this test. Several types of family and community bomb shelters were also tried out. The blast from the 16-kiloton shot hits the house at 3,500 feet, around 3/4 of a mile, almost total destruction. The other house at 1.5 miles showed only moderately heavy damage. These visually spectacular tests were only one portion of a big program which included extensive dosimeter and radiation research and important biomedical and genetic studies by some of the country's top scientists. The second major phase of the 1953 series, military effects tests, was, from the service point of view, the main feature of the show. All early planning and coordination of these tests was handled by the Directorate of Weapons Effects Tests, set up for this purpose by Field Command, Armed Forces Special Weapons Project. In the operational phase, personnel of this directorate were integrated into the main test organization. There, they continued to be responsible for all military tests and for the important military support given to the AEC's programs. Such support, for example, as the Air Weather Service forecasts, on which are based the fire or no fire decisions for each shot. The bulk of the huge knothole program was carried out on Frenchman Flat, though some military tests were run on the weapon development shots up on Yucca. Number 9 on 8 May was the first knothole shot, an airdrop of a 26-kiloton weapon. All military tests on Frenchman Flat were originally built around this shot. The relatively high burst height, 2,400 feet, was a compromise to fit many tests, rather than to inflict maximum central damage. Shot 10, 25 May, proof-tested another delivery system, the Army's 280-millimeter gun. When this shot was added to the program, some additional effects tests were scheduled to observe results of the low burst height, approximately 520 feet above ground. Since no gun-type assembly had been detonated since the Hiroshima bomb, the weapons development scientists had on this shot their first opportunity to study the nucleonic behavior and fireball configuration of such a device. Yield 15 kilotons. Unlike the situation with an implosion weapon, the scientists were here able to observe fireball growth from a body of fissionable material whose exact shape and dimensions at the moment of detonation were known. As scheduled, the military effects tests total well over 70 distinct projects under 9 major program headings. Headings which might in a sense be considered as signposts guiding us along our road. The road full of questions that we followed through Knothole, one of the biggest military test programs in our records. To begin with, we wanted more and clearer data on blast and precursor phenomena, and on the Mach stem, and the triple points path. We wanted enough data to predict what these factors, plus thermal and nuclear radiation, will do, of military significance, to any living being or object they can reach. These were the objectives of our road. We haven't the time to stop for a look at every signpost along the way. We'll just have to hit some of the high spots and new spots. A project, for instance, that didn't use a new technique, but that hadn't been covered in previous report films, had for its aim to measure free field blast pressures in regions of concern to delivery aircraft, and to determine the triple point height in at least one location. Two B-29s did the muscle work on the job. Just before shot 9, they dropped 14 canisters in the target area, timed to be hanging on their parachutes at burst time in a long line some 5,000 feet high and spaced out to nearly 7 miles from the burst point. Each canister telemetered its altitude and surrounding air pressure to a ground station tape recorder. The tape also marked time of burst and time of shock arrival at the canister. The close-in canisters each received 2 kicks, one from the incident wave and one from the reflected wave. Farther out, each canister received a single kick from the Mach stem, indicating that the triple point where the 2 waves merge had sliced up through the canister line at a distance and altitude that we could compute from the recording tapes. In the nuclear radiation program, particular interest centered on Shot 10's neutron flux measurements, the first ever made on the detonation of a gun-type assembly. Gold, tantalum, and sulfur threshold samples were used to detect neutron energy levels from thermal to around 10 million electron volts. The total flux per kiloton was the highest ever observed, running 10 to 30 times as high as the implosion shots 8 and 9, and extending the median lethal radiation range some 600 feet. One novel feature of Upshot-Knothole was the first use of drone aircraft on a Continental atomic test. Navy AD-2s were instrumented for blast and thermal radiation response and were flown at near critical distances from several bursts. Results indicated that comparatively moderate thermal inputs may seriously reduce the blast resistance of some aircraft components. Standard blue aircraft paint proved clearly inferior to white or unpainted metal surfaces for protection against destructive thermal effects. Similar flights by manned and instrumented Air Force B-50s and a B-36 gave structural response data needed to establish minimum safe operational parameters for high-performance bombers. Other bombers from the Strategic Air Command flew in with the drop plane, testing techniques for obtaining yield, height of burst, and ground zero location, the 3 essential parameters of IBDA, indirect bomb damage assessment. On the biomedical program, Air Force QF-80 drones instrumented to measure gamma radiation and with test animals aboard were flown through atomic clouds at 30,000 and 32,000 feet. They were each controlled by primary and secondary motherships, and manned fighter escorts stood by to shoot down any drone that malfunctioned. These tests indicated that personnel of pressurized aircraft passing at 400 knots through a cloud at least 4 minutes old from a weapon of less than 30 KT would receive an external dosage of less than 50 Roentgens, with a negligible respiratory hazard. On the thermal effects program, one project concerned parked aircraft and aircraft components, an extension of previous tests. New data were obtained on structural weakening from thermal inputs too low to cause visible damage. Cloth thermal shields were proved to have considerable value in reducing damage to parked aircraft. Some aircraft fabrics were destroyed at levels as low as 2 calories per square centimeter, while magnesium sheet and foil-covered panels were undamaged by 20 calories. It was also found that strong tie-downs may protect aircraft parked nose-on to the blast from much of the damage that will occur if the plane is unmoored and free to lift and roll. But for side-on or tail-on orientations, the tie-downs may actually increase damage. Another important section of the thermal program was a study dealing with normal city vulnerability to fires started by atomic weapons. 3 cubicle houses 7,700 feet from zero were erected for one phase of this study concerned with exterior kindling fuels. The first house has a clean, safe yard, but dry rot is working in the unpainted siding. No rot here, but toys, weeds, and trash against the fence. A clean yard, painted fence, and maintained siding. Number 9 goes off. 13 calories per square centimeter. Overpressure 3.5 pounds per square inch. Time sequence photography shows the results. Destruction on the right from the yard trash which set fire to the fence. On the left, rotted wood in the siding was the ignition point. Sound painted wood and a clean yard allow the center house to survive. The fire hazards in these projects are not unusual either. 6 big American cities were inspected to ensure that representative conditions were tested. Conditions which suggest that a bomb of even this nominal power could start more than 100,000 fires over 25 square miles of urban area. Our next thermal project, run on Shot 10, required a new instrument line east from ground zero, roughly opposite the main blast line, equipped with thermal recording devices and with blast gauges at 0 and 10-foot heights. The first phase, designed to find out how much protection white smoke would give against thermal flash, employed a standard oil fog over a portion of the new line. In theory, this smoke would scatter and reflect fireball heat. This was a small-scale experiment, but evaluations have indicated that attenuation of radiant energy approached 99%. To explain the second phase of the project, employing black smoke, we must go back to Tumbler Snapper. On the low-altitude burst of Tumbler 4, high-speed cameras recorded a phenomenon never noticed before, a shock wave preceding the main shock front. Here it is again. This precursor wave, as it was called, registers on blast line instruments with a pressure time graph of this type, showing a considerable climb and duration before arrival of the main shock front. A normal shock wave with no precursor is quite different, hitting the instruments with an instantaneous pressure jump. The mechanics of precursor development appear to be these. A weapon bursts, and thermal radiation creates an intensely hot ground layer of air, a layer filled with dust from what is called the popcorning of the hot ground. Milliseconds after the thermal flash, the incident shock wave reaches the ground and expands, trailed outward by the usual reflected wave. Then a new wave, the precursor, begins to build out from the base of the incident wave, racing ahead through the heated air layer. An intense dust cloud follows closely, rising initially to about 50 feet and later to several hundred feet. One important effect of the precursor is to lower peak static pressures without a corresponding reduction of dynamic or wind pressures. The precursor builds steadily in height, but does not seem to inhibit formation of a Mach stem, though exact dimensional relationships are uncertain. Eventually, running into cooler regions, the precursor slows and is overtaken by the Mach stem. From that point on, the blast wave structure is normal again. It should be emphasized that a precursor can form only if the ground air layer is sufficiently hot. So if height of burst is increased, yield must be increased. Without the yield increase, the ground air will be too cool for precursor formation, as was the case on Shot 9, our first effect shot, 26 KT at 2,400 feet. Shot 10, 15 KT at only 500 feet, developed a strong precursor. It was on this shot that we ran the smoke experiment. A carbon black smoke was established over nearly a mile of the new instrument line. We expected that the top of the black smoke would absorb thermal energy and produce an extra hot layer well above ground, possibly generating a controlled super precursor at that height, or in some other manner reducing blast effects on ground targets. The experiment was handicapped to an unknown degree by wind billowing the smoke up to 300 or 400 feet, modifying the planned geometry. As it happened, the ground level precursor which developed under the smoke was stronger than the one in the clear, although it extended only half as far before decaying to a conventional blast form. This test was not conclusive as to the effects of a heat-absorbing black smoke on blast. A further precursor study was set up to determine whether ground surface heating from thermal flash could generate a shock wave before arrival of the normal shock front. Panels 10 feet square, faced with variously heat-absorptive and reactive materials, were tilted for maximum exposure to the thermal radiation of the two effect shots. Post-shot study of the gauge records showed no clear evidence of thermally induced shock waves. We come now to the biggest program, the primary reason for Shot 9, the first effect shot. The biggest program in sheer volume, in theoretical predictions confirmed or refuted, and in the mass of empirical knowledge gained. 28 separate projects came under this heading, beginning with basic measurements on simple cylinders and rectangular concrete slab structures in a number of orientations. These passive targets, heavily instrumented, were not designed for response by displacement, but only to record shielding and loading factors at various heights and aspects. The findings of this important job can now be extrapolated for prediction of blast loading on a great variety of targets without direct testing. We begin to bump into the precursor again. A truss bridge section 2,300 feet from zero. Shot 9, 26 KT, 2,400 feet high, produced a small permanent set in the top chord with an overpressure of 11.5 pounds per square inch. But the mock stem had not formed to reach the height of the bridge. 8.5 pounds did this on Shot 10, 500 feet high, 15 kiloton yield, with a precursor blast wave and a mock stem already higher than the bridge. Apparently, for wind or drag-sensitive targets of this type, a low burst is more damaging than a high burst at similar peak pressures. A test of Army prefab Bailey bridges. Shot 9, 4,100 feet from zero. Essentially undamaged, the bridge slid back on its piers as expected, moving 43 inches from a peak pressure of 8 pounds. 9 pounds from Shot 10 hits another bridge. Movement out of all proportion to that caused by almost the same static pressure on the first shot. Army equipment, which included 54 trucks and jeeps, was exposed to Shot 9 pressures ranging up to 21 pounds to the inch. Thermal input reached 130 calories per square centimeter. Damage was generally moderate, as expected. All but 2 vehicles, one with burned tires and one with a missile-punctured radiator, could be driven away under their own power. For Shot 10, Army tanks, artillery, and 22 trucks were exposed to pressures expected to range from 3 to 55 psi. Once more, damage was much greater than expected. Equipment was not merely overturned, but often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on Shot 9. Obviously, Shot 10 was handing out surprise data. It was evident that our old static pressure criteria were not valid for predicting damage to wind-sensitive targets in the precursor region of low bursts. Not only were there violent high-frequency pressure fluctuations in this region, but the precursor depressed static pressures no longer had the same relation to dynamic or blast wind pressures found in a normal shock wave. Standard command posts, foxholes, and machine gun positions were located on Shot 9 at 600, 800, and 4,000 feet from zero. Overpressures 8 to 22 pounds to the inch. General analysis indicated that cover-supporting timbers began to fail at 8 psi, while revetment stood up to around 20 pounds. Conventional sandbags tended to catch fire and spill their contents. One interesting finding was that foxhole covers can greatly reduce inside pressures, which may otherwise build to twice the outside pressure. Field hospital installations were displayed for shot 9 at ranges around 4,400, 9,000, and 15,000 feet, in both above ground and dug-in positions at each location. Radiology sections, operating rooms, pharmacy tents, all complete and ready for use. 38 calories per square centimeter. 8 pounds per square inch. Operationally, a complete ruin, although a few items of equipment were salvageable. Missile hazard was unquestionably heavy. The 15,000-foot installation, around 1 1/4 pounds pressure. Damage limited to collapse of the above-ground tents. A significant finding of these tests was that considerable protection to personnel and equipment would be afforded by revetting field medical installations. 6 Marine LVTs, landing vehicles tracked, at distances from 800 to 4,500 feet from zero, with pressures reaching 22 psi, 2,400 feet, overpressure 11 pounds. Damage was light on all vehicles. On shot 10, the same vehicles varied from 1,000 to 3,450 feet from zero, pressures running up to 47 pounds. Shot 10 damage was again unexpectedly heavy as compared with shot 9, with 1 vehicle destroyed and 3 severely damaged in the precursor region, which on this shot extends out to around a half-mile from ground zero. These tests suggest that normal shock waves from high bursts will damage LVTs only moderately up to 22 psi, while low bursts will do severe damage above 12.5 pounds. Curtain wall panels on a series of concrete test cells, some with window openings, some without. The panels were constructed of various masonry materials such as brick, cinder block, clay tile, and combinations of these materials. Similar variety went into roofs and interior partitions. On shot 9, 4.5 pounds overpressure does this, 6,700 feet from zero. 7 pounds here, 4,400 feet range. Unreinforced brick stood up fairly well, though cinder block and transite shattered. Walls with 20% window opening showed much greater blast resistance than blank walls, though damage to interior partitions was high. 3 framed structures with windows and skylights containing various types of glass and plastic glazings were set up at 7,600, 12,500, and 20,000 feet from shot 9. Pressures were 4 psi or lower. A few conclusions that can be drawn now are that 1/4-inch clear plastic shattered least of the material tested. 1/4-inch wire mesh was the largest mesh effective in reducing interior missile hazard. Exterior jalousies were worthless, and explosion hardware has very limited usefulness and may even be disadvantageous. Signal Corps placed radial and transverse pole lines, underground wires, and aluminum towers at different distances to test damage effects and determine time required to restore communication facilities. On shot 9, pressures of 7 to 9 psi knocked down the transverse pole lines at 3,500 and 4,500 feet and partially destroyed lines at 5,500 feet in the 5-pound region. However, radial pole lines end-on to the blast were almost undamaged. Similarly, towers at 3,400 and 4,400 feet were knocked down, and the one at 5,400 feet heavily damaged. At 6,400 feet, the top section of this 240-foot tower was made unsafe by 4.5 psi. Shot 10 damage to these installations was much heavier. The blast winds destroyed even the radial pole line to 2,500 feet, with static pressures by which it was undamaged on shot 9. Air Force, Marine, and Quartermaster POL installations were given extensive testing. The major items were 5 and 55-gallon drum stacks, bulk storage tanks, and various subsidiary items such as can cleaning, metering, filtering, and pumping equipment. In general, Shot 9 damage was light or insignificant. There were minor gasoline fires. Drum and can stacks were scattered slightly in the maximum pressure areas, around 16 psi. 2 collapsible 900-gallon tanks were ruptured by 11 pounds at 2,600 feet. On Shot 10, results were unexpectedly violent. All stacks disintegrated, with cans and drums thrown hundreds of feet and left flattened or badly crushed. All marine fuel handling equipment was destroyed except 1 collapsible tank. Almost complete destruction occurred at better than 2,000 feet, at the same pressures that did trivial damage on Shot 9. A study of tactical importance. 145 ponderosa pines set in concrete, approximately 6,400 feet from Shot 9's 0. Instrumentation was thorough. A few major types being pressure gauges at 3 heights, time recording anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Pendulums were substituted for the lollipops of former operations to provide mechanical simulation of tree response. As on many of these projects, camera stations were set up to provide high-speed motion picture coverage of blast effects. Thermal input, 18 calories per square centimeter, resulting in only mild char on tree trunks, since the normal ground litter that will ignite at around 3 calories was lacking. Static pressures around 4 psi. Post-blast survey indicated that approximately 20% of the trees were broken, and the missile hazard from falling trunks and limbs would be substantial. There was scant reduction of static pressure inside the stand, but a 20 to 40% reduction of dynamic or drag pressures. Thermal shielding proved excellent, with negligible penetration beyond the 4th row of trees. 16 items of Army rolling stock were exposed on Shot 10 only. A 45-ton diesel locomotive, 1 riveted and 1 welded steel tank car, 13 boxcars loaded and unloaded of various types, 6,600 feet, 2 pounds overpressure, 4,400 feet, 4 psi, 1 empty boxcar turned over, 1 loaded car damaged, 3,400 feet, 6 psi. Boxcars damaged or overturned. 2,800 feet, 7.5 pounds. 1,850 feet, 9 pounds. 1,500 feet, before being hit by 13 pounds to the inch. And here's the same view afterward. The frame of one of those tank cars was thrown against a building 200 feet away. A tank car body went 1,200 feet. The whys and hows of these excessive damage effects at static pressure levels where no such results were anticipated will require further study, as will the mechanics of precursor development over surfaces less suited to the development of heated ground air than the Nevada desert. While to date these damage effects have been observed in the precursor, it does not follow that attack conditions should be chosen to maximize precursor formation. Such effects may be characteristic of any low burst, without regard to precursor phenomena. Although high bursts are still required for optimum damage on many important targets, the tremendous destructive force of a low burst has brought about an interim restatement of damage criteria for drag-sensitive targets, and was the most important single finding of the military effects tests of Operation Upshot-Knothole.